Audio Jungle. Audio Jungle.
So we had seen that momentum equation, okay, and that momentum equation we had seen in integral form last class, okay. So what was the momentum equation? Momentum equation in integral form, and it was dou by dou t triple integration rho v vector volume v plus surface integral, this is the volume, okay, v vector ds into v vector equal to minus pressure force, this is the surface integral, plus this was body force plus Fp viscous force. This was the momentum equation that we had discussed in last class. Yes or no? All right. This is the volume integral, and it is especially it was mentioned. This was the pressure force, and this was the body force, and this was the viscous force. All right. Now, this also can write in differential form. This momentum equation because this is the integral form. Okay. So in integral form also we can write in short. So if we write this momentum equation in integral form, okay, then this can be. Next slide I will write. So this will be, we can write momentum equation in differential form. Okay. That will also be called as Navier-Stokes equation. What it is called? Navier-Stokes equation. Okay. Navier Navier-Stokes equation. What it is? Dou by dou t rho u plus grad rho u v vector dp by dx rho gx, which is nothing but viscous force. So this is basically in that x direction. X direction, that's the reason u component only you are getting here, x component you are getting dp by dx. Okay, that pressure force. Similarly in y direction, if you write in y direction, it is dou by dou t. Instead of mu, it will be small v, rho v. Okay, in bracket rho, instead of u, it is small v, then capital V vector is equal to, instead of dou p by dou x, it will be now in y direction dou p by dou y, plus rho body force will be g y instead of gx, and viscous force will be fy. Okay, similarly in z direction it will be dou p by dou t. In z direction, what is the velocity component? W, rho w, plus operator in bracket, instead of v, it is z direction w, v vector, instead of dou p by dou y, it will be dou p by dou z now, plus similarly gy will be in z direction dou gz, plus f will be fz viscous force. So basically this is what differential form of the momentum equation. Directly I have written, you need to remember it, okay, because if we'll go again derivation, then it will be the very lengthy process. That integral form I have shown you. Similarly you can write this integral form. Okay, so this like Navier-Stokes equation or momentum equation in differential form in x direction, y direction and z direction respectively will be valid for all type of flow. It is valid for steady flow, it is valid for unsteady flow, it is valid for 3D flow, compressible or incompressible, viscous or inviscid flow. Okay, if you say inviscid flow, then viscous force will be removed. If you say steady flow, then dou by dou t will be removed. But if you are not removing anything, it means it is valid for all type of flow. Yes or no? So here you can write valid for, okay, that Navier-Stokes equation, NSE, Navier-Stokes equation or momentum equation in differential form, valid for point 1, valid for steady or unsteady, valid for 3D flow, okay, only 2D, 3, all type of flow. Okay, basically here what I have written in XYZ, so it is 3D, but if it is 1D or 2D, accordingly you can remove the dimension. Then it is valid for compressible or incompressible, is valid for viscous or inviscid flow, valid for rotational or irrotational flow. So this is the validity of the equation what we have seen. Okay, so need to remember it. Now if you go for the like condition, if you apply, like if you are writing momentum equation for steady and inviscid flow, then what will happen? Okay, can mention momentum equation momentum equation for steady, okay, inviscid with no body force. You can write like this. All right. So if you apply this condition, then what is the mean of it? Check. Steady means what? Anything with respect to time derivative, anything you can write here. That will be zero. Inviscid means what? That viscous force, viscous force, F will be zero. No body force means what? What is the body force? Gravity force. So that gravitational acceleration will be zero. So in this previous equation, any you have here, this is the x direction, this is the y direction, this is the z direction. Okay, so all three equation, if you apply what you have written, steady, so that dot term will be zero. Okay, if you are writing x, y, z, so dot term will be zero. If you are writing no body force, so gx, gy, gz will be zero. Okay, you are saying illicit flow means viscous force will be zero. So you make it fx is equal to zero, fy is equal to fz is equal to zero. Okay. So if you write this, then this equation will be what? This illicit force means fx will be zero, fy will be zero, fz will be zero. Similarly, gravity force gx will be zero, gy will be zero, and gz. So if you write the same momentum equation here, okay, for x direction, what you will have? Check what component left now. Only this component and this component will have. Yes or no? Similarly, here this component you will have and this component you will have. Similarly, here this component you will have and this component. All right. So you can write now your momentum equation will be this is the momentum equation. If you have mentioned steady, inviscid, and no body force. Okay. These are the momentum equation. Okay. For steady, inviscid with no body force. I told you that when body force will be removed, then what will be happened? Huh? Okay. So let us see one by one. I will discuss you. So now this is the equation. If you have removed the body force, you have considered inviscid flow and steady flow, then this will be the basically equation. Okay. All right. Now the same equation you can write if you open the bracket gradient and all. If you open, then what you will get finally? Okay, what you will get, because check again, it is the bracket part, no? That operator dot in bracket rho u v vector. Okay, so is equal to minus dou p by dou x. So this if you open, then finally you may get, if you open this and if you satisfy the streamline equation, then finally you can write or or the same you can write x direction, you can write u du is equal to minus, this is the step you have to perform, dou p by dou x into dx. Similarly, y direction, if you open the bracket, v, okay, dv minus 1 by rho dou p by dou y into dy. Z direction it is w dw is equal to minus 1 by rho dou p by dou z into dz. If you add all three, okay, if you add all three, then what you will get? If you check this equation also, you can write u du. What you can write? You can write 1 by 2 du square. If you differentiate this, then what you will get? 2u into du. So 2 cancel out. So again you will get u du, right? Is equal to minus 1 by rho dou p by dou x into dx. Similarly, this equation you can write 1 by 2 into v square minus 1 by rho dou p by dou y into dy, and this equation will be 1 by 2 d w square minus 1 by rho dp by dz. All right. If you add all three, if you add this, then what you may get? Okay. After adding all three equation, what you may have? You may have, okay, if you are adding all three, then you may have 1 by 2, yes or no? D in bracket u square v square plus w square is equal to, you may have minus 1 by rho in bracket, what you can write? Dp by dx dou p by dou y dy dou p by dou z dz. You can write this. Then what is this? This is nothing but 1 by 2 d into u square plus v square plus w square is nothing but resultant v, capital V you can say, okay, is equal to minus 1 by rho. What is this? Dou p by dou x into dx. This is the total. If you know the total derivative concept, so this is the partial one. If you write total, then total will be what? 1 by rho into dp. This whole thing. How you can write? You can say p is the, okay, p is the function of x, y, z. Then what will be dp? Dp will be dou p by dou f into dx. Dou p by dou y into dx. So this is what? Total derivative. What it is called? Total derivative. Similarly, v vector, I told you what is the v vector? ui vj plus wk. I told you this uv vector in last class. This is the x, y, z. In x direction, what is the velocity u? In y direction, what is the velocity v? And in z direction, what is the velocity w? Okay. This is I vector, this is j, and this is the k. Okay. Unit. Now, if you write the resultant, so what you may have? You may have q square, v square, and w. What will be the v square? It will be, so check, Instead of u square v square plus w square, I have written v square. Instead of dou p by dou x df, dou p by dou y dy, dou p by dou z dz, I have written dp. So hope you understood this. Now what you have now, you have this equation. I can rewrite again. So this is nothing but 1 by 2 d capital V square. This is capital V. Okay, is equal to minus 1 by rho into dp. All right. Again, if I solve this, then what I can get? 1 by 2. If you differentiate v square, so what you will get? 2v into dv is equal to minus 1 by rho into d. 2 to cancel out. What you may have? It is v dv minus 1 by rho dp. Or what we have? v dp plus 1 rho by dp equal to 0. Yes or no? Check this equation. So what we can write? We can write dp by rho plus v dv. What it is called? What it is called? It is called Euler equation. What it is called? Euler or Euler's, whatever you can call Euler. Okay. It is valid for. It is valid for what? It is valid only for steady flow. It is valid only for inviscid flow. Okay. It is valid for compressible and incompressible. Valid for both. Okay. And what forces available for this? Only pressure force. How to know it is valid for steady flow in viscid, or like how you would say? Because you have taken the assumption. What was the assumption you made? You made assumption steady, you made assumption in viscid, you made assumption no body force. No body force means gravity force 0. Inviscid means viscous force 0. So what is the force left? Only pressure force. So here I have mentioned, no? Only pressure force, because it is in derivative form. So compressible and incompressible both, it is valid. Okay. Only for inviscid flow because the assumption you have taken, and only for steady flow because already you have taken assumption. This is important. So this is called as Euler's equation. All right, Euler's equation. Now, how to get the Bernoulli equation? How to get Bernoulli equation? This is the Euler's equation. Okay. So here I can write next heading called Bernoulli theorem. So this is basically based on energy conservation, Okay, first of all, huh? I can write here based on energy conservation, and it is valid. Okay, it is valid only for what you can write. It is valid only for incompressible study. First we need to write a study, valid only for study flow, and valid only for incompressible flow. Okay, and it is valid for in-viscid flow. Need to remember, this is very important. Okay, fine. Two things are there: valid along the streamline. What is the streamline? Will tell you. Or throughout flow field. And in what is the mean of it? Its mean is it can be valid throughout the flow. Means in the flow anywhere you can apply, or only along the streamline you can apply. There are the conditions, so that we'll discuss later. Okay. Now, so how to get Bernoulli equation? So you have Euler. You have Euler equation, right? So if Euler's equation is integrated along the streamline, for constant density, which means incompressible fluid, then it will be called as Bernoulli equation. Okay. Bernoulli theorem is what? It is based on energy conservation. Throughout the flow, energy will be conserved. That is the theorem. How to get the equation? So we have Euler's equation. What is the Euler's equation? We have Euler's equation dp by rho plus Vd is equal to 0. If you integrate, if you take 2 points and if you integrate between 2 points, okay. So we can write this Euler's equation. We have, what is the Euler's equation now? dp by rho. Okay. But we need to write integration from point 1 to point 2. So you may have that 1 to 2. What is that? dp by rho 1 to 2. And if we have elevation, Okay, if we have elevation also, so we can write g dz, okay, for the elevation. If we have elevation, then we can write g dz, and that we can integrate 0.122. Okay, if you integrate this, after integration you may have a constant if you get the result. Yes or no? This is now conjugate. Okay, this portion extra I have added. Okay, this portion is called potential energy. When there is the elevation will come. Okay, if there is no elevation, so definitely potential energy will not be there. Elevation change. Okay, if elevation changes are there, then it will be in the picture, otherwise it will be removed. If there is no elevation, I mean it is on the same surface, then definitely potential energy will be zero. This part will be what? Kinetic energy, and this will be what? Pressure energy. Okay, fine. Now, so if you check this, if you integrate this, finally what you may get. Now, now if you integrate this, what you will get? You will get P by rho plus, what is the VdV? VdV is nothing but V square by 2. If you want to write limit 1 to 2, then you can write V2 square minus V1 square, V2 minus V1. Otherwise, you just integrate simply, and this right value. This is nothing but plus Gz is equal to 0. Sorry, constant. Yes or no? This is what? This is the Bernoulli equation. Okay? This is the Bernoulli equation, which is based on energy conservation. Okay? Now, again, you can write in different format. What is the another format you can write? If you check the unit here, okay? So, this is what? This is the kinetic energy. Huh? mv square by 2 is kinetic energy, but mass is not there. So, this is the specific kinetic energy, which is nothing but, what will be the unit here? The unit will be what? Joule per kg. What is the unit here? Joule per kg. And what is the unit here? Here also it will be joule per kg. So basically, joule per kg is what is specific energy. Okay, specific energy, or you can say this is the Bernoulli equation. Okay, let me write here. This is the Bernoulli equation. What I can write? I can write energy per unit mass. Okay. Similarly, the same equation I can write. How I can write? I can write P by rho g, because right side is constant, so we can divide by g throughout the equation. So it is P by rho g v square by 2g plus, this is also Bernoulli equation. Now check the unit. What is the unit? See, generally what is the kinetic energy? Half mv square. So this is the v square by 2g. Mass is not here, so becomes specific or energy per unit mass. Now it is divided by g also, so mass into g is nothing but weight. So it becomes unit, if you check, it becomes joule per Newton, because it is the weight now in denominator. This is also joule per Newton. Okay, and obviously this will also be joule per Newton. So now this is also kinetic energy. Okay, this is also Bernoulli equation, but this Bernoulli equation is what? It is energy per unit weight. All right. Again, the same Bernoulli equation you can write in another form. You can write P plus 1 by 2 rho v square plus rho gz is equal to constant. Check the unit. This is what? If I will take this half rho v square, so what will be the unit? This itself, this is nothing but, you can take or you can write the unit anywhere if you want. What is the rho? It is mass per unit volume, means kg per meter cube. What is g? It is meter per second square. What is z? It is meter. If you write the unit for all, similarly this one half rho v square, anyone I can write. So any like I can try half rho v square. So 1 by 2, it is constant. Rho is nothing but mass per unit volume, kg per meter cube. What is the velocity? Meter per second square. So I can write kg. This is kg per meter cube. This is meter square. So we'll get meter square cancel out. So this is kg per meter into second square. Yes or no? Kg per second square meter. Similarly here also rho gz. Okay. What is the rho gz? This is nothing but density, kg per meter cube, g is meter per second square, and then you will have z. Okay, which is nothing but meter. So overall